This is AP Calculus 6-9, integration using substitution. And we kind of hinted before that there was a chain rule for integration. They don't really call it the chain rule, but this is the way to go backwards. When we have used the chain rule to find the derivative, we can use U substitution to go backwards and go back to the original function. So that's what we're going to talk about today. Remember the chain rule. If I ask you to take the derivative of something where you've got an expression inside parentheses to a power. Remember when we did the chain rule, we took the 3 multiplied by the number in front. So 1 times 3 is 3. Then we keep what's inside, decrease the power by 1, and then we take the derivative of the inside part, which is a 2. So we end up with 6 times 2x plus 5 squared. So if we want to go backwards from this, in other words, we want to take our answer, what we got when we used the chain rule, and go backwards to find our original function, we can do that using something called U substitution. Notice here, when I rewrite this with the integral symbol, the only way I could do that right now is by taking out the 6, we could FOIL this and then do each term separately. But that's going to be time consuming. And especially if you have something here that is to a power higher than 2. You know, 2's, the second power is not too hard to do, but if you had a 4 or 5 or a 6 or 10 there, you wouldn't want to FOIL that to be able to find the integral. So there's got to be an easier way to do it. So we're going to start with an easy problem like this and work our way up to the ones that are more difficult. And notice here, I've got this extra dx here. Whenever you're taking the integral of something, you are going to have that dx, and remember, that represents the thickness of our little rectangles that we're drawing underneath the curve. It really doesn't mean a whole lot yet, but when we do U substitution, that dx is going to become important. So we're going to talk about how to use that. So the first thing I'm going to do with this one is I'm going to decide what U needs to be. We do a U substitution, and so in other words, we're going to take U and replace something in the original problem with U to make it easier to find the antiderivative. And keep in mind, these are antiderivatives. They are not definite integrals. They do not have the boundaries here. So since this is an indefinite integral, all of these answers will have to have a plus C because we are not accounting for the whole number part that may have been added to this if we don't have those intervals. So I'm going to, for this one, let U equal, and almost always when you're doing U substitution, your U part is going to be what's inside the parentheses. What was the inside part in our original function here. So I'm going to let U equal 2x plus 5. Now, whenever I do U substitution, I can't just substitute U, I also need to do a du. So if this is U, du is the derivative of what we chose for U. So if I take the derivative of this, the derivative of that is 2, and I need to tag that dx in there. Because what I'm going to do is everything in here has to be substituted with some form of U, whether it's U or du. 2x plus 5 is U. So I can replace 2x plus 5 with U. So I've got U squared dx. Now, I can't integrate this till all my variables are U's. I have a dx here. I need to replace dx with some form of du. In order to replace dx with du, I need a 2 dx here. Well, I've got a 6 dx. But we learned that we have properties that allow us to take whole numbers out if they're in there. So I need this to be a 2. So I can take a 3 out, put it on the outside, and force that to be what I need it to be. So I'm going to bring a 3 out. I'm going to leave that 2u squared dx. Now I have the 2 dx that I need to put the du in there. That 3 can be outside or inside. It doesn't matter, but I'm going to put it outside to make my u substitution. So I've got the 3. 2 dx is du, so I've got u squared du. Now, think back when we first learned how to do integrals. That's a very, very simple integration. To solve that, I keep my 3. That's going to be u cubed over 3 plus c. we have taken the antiderivative. That 3 and the 3 on the bottom cancel. So I'm going to move it up here, u cubed plus c. The next thing I do is go back and resubstitute what u was in the original problem. So u is 2x plus 5 cubed, and we've got the plus 3 to account for any whole number that may have been added to our function. Look at this. That's 2x plus 5 cubed. Notice right here, 2x plus 5 cubed is what we started with. For our next one, I've got the integral of 2x, x squared plus 1 to the 4th dx. My u, I'm going to let x squared plus 1 represent my u. My du will be 2x dx. So let's look at what we've got here. This is my u. So I've got the integral of u to the 4th. My du is 2x dx. So I've got u to the 4th du. Once I've done the substitution and I've got everything in terms of u, I can integrate. That's u to the 5th over 5 plus c. And then if I resubstitute, I've got 1/5 times x squared plus 1 to the 5th plus c. You can always double check and take the derivative of this to see if they match. If I take the derivative of this, 5 times 1/5 is 1, times x squared plus 1 to the 4th, times the inside part, 2x, and then they tag the dx. So you can always check these to make sure you're getting them right. For this one, I'm going to let u equal x squared plus 1. And notice this one's very similar to the last one, but it's missing that 2, so we need to deal with that. So I've got my u, x squared plus 1. Du is going to be a 2x dx. Well, we almost have everything we need, but this function needs a 2 in front of the x in order to have the full 2x dx. What we're going to do is we're going to force this to have what we need and offset it with its reciprocal. Let me show you what I mean by that. We have the x squared plus 1 that we need for our u. We have our dx. We have our x. But what we don't have is this 2. So I need to force there to be a 2 inside here. Well, if I put a 2 in there, I have to offset it with the 1/2, because 1/2 times 2 is 1. I haven't changed the value of the problem by doing that. I've just made it look different. And we're always allowed to do that as long as we're dealing with numbers. Now, if this had an extra x there or something like that, we couldn't do this. We'd have to do something different. All right, so we can only do that with numbers, keep in mind. So I can multiply by a number and then multiply the outside by its reciprocal to change what it looks like, but I haven't changed its value. So now I'm going to do my substitution. I've got the 1/2, the integral of u to the 4th du. Now I can take the integral, that's u to the 5th over 5 plus c, and that would be 1/10. U to the 5th would be u is x squared plus 1 to the 5th plus c. Sometimes we'll have trig functions that we have to deal with. When you have trig functions, you need to look for the derivative of one of the functions. So think about the function you have and what its derivative would be. Now, if you think about secant squared, the derivative of secant is secant tangent. I don't have a secant tangent here, okay? And that's a secant squared, so that would be a secant squared, so we need to use a chain rule for that. So we don't have the derivative of secant. Let's think about tangent. Do we have the derivative of tangent? The derivative of tangent is secant squared. So derivative of tangent is secant squared. I would let u equal the tangent x plus 3. So my u is tangent x plus 3. That means my du, the derivative of tangent, is secant squared x dx. Here we have a secant squared x dx. Here we have our u, tangent x plus 3. So that 2 can be brought to the outside, and then we can substitute. That's u du, u du. If I integrate, I've got 2 times u squared over 2 plus c. The 2's cancel, leaving me with u squared plus c. So tangent x plus 3 is my u. The original problem had that squared, and we've got a plus c. And again, you could take the derivative of that to check it. So I'm going to do that real quick. 2 times 1 is 2. Keep the inside. Decrease that power by 1. Derivative of the inside is secant squared x. That is what we started with in the beginning. So we know we got it right. Here are 2 problems. I want you to pause the video, see if you can get the answer to these on your own, and then I'll give you the answers in a few minutes. So here are those answers. I've separated them with a line here so you can tell the difference. Here, I let u be 2x minus 1. So my u is to the 1/2 power, which I substituted here. If I take the derivative of 2x minus 1, I end up with 2 dx. I have the dx, but I don't have the 2. So I need to put the 2 in there. I offset it with the 1/2, so I've only multiplied by 1. And then I can do my u substitution. U to the 1/2 du. I take the integral, that's u to the 3/2, over 3/2, which is times 2/3. The 1/2 and the 2 cancel, leaving me with 1/3. 2x minus 1, that's u to the 3/2, so 2x minus 1 to the 3/2, plus c, our constant. In the next one, trig functions tend to cause a little more trouble than usual, but that's okay. Here, my sine, you understand hopefully that the derivative of sine is cosine, the derivative of cosine is negative sine, right? Usually if you have a sine and cosine, the 1 to the power is going to be your u. That's just something you'll learn as you do more of these. So I'm going to let u be sine 3x. Now if you think about taking the derivative of sine 3x, du would be sine, the derivative of sine is cosine 3x, times the derivative of the inside part of 3. So my du is 3 cosine 3x dx. Well, I have the sine 3x, so that u would be squared. I have the cosine 3x dx, but I don't have the 3, so I need to put the 3 in front, offset it with a 1/3, so I've just multiplied by 1. Then I have u squared du. Keep the 1/3 outside. Take the antiderivative, u cubed over 3. 1/3 times 1/3 is 1/9. And we've got sine cubed 3x, replacing the u with what it equaled, plus c. And you can take the derivative and double check and see that you start with the same thing. For this one, I'm going to let u equal x squared plus 6. So du will be 2x dx. Notice I have a 5x dx. Now, what I'm going to do there, since like before when this happened, I had a 6 here, so I could bring the 3 out, keep it a 2. I can't do that here. So what I'm going to do is I'm going to take the 5 out, which leaves me with this. Now, I need a 2 in front of my x. If I put a 2 in front here, I just offset it with a 1/2 on the outside. I'm allowed to do that. So what I end up with on the outside is really 5/2. And 5/2 times 2 does give us 5, so we know that works out to what we started with. And then I'm going to do u substitution. That's u to the 5th du, and I integrate. So we have 5/2 times 6 is 5/12. U is x squared plus 6 to the 6th plus c. And again, you could integrate, make sure you end up with the same thing at the beginning as you would if you integrate that. So not too bad. It is a little different. The best way to get good at this is to just practice.